Hi, in this video we are going to see about Rotary Encoder. If you don't know anything about Rotary Encoder, how it works, what are its output signal, how to interface it, how to write code for it, don't worry, we are going to see everything in this single video. What you see, this teeny thing in my hand is called as a Rotary Encoder. It looks like potentiometer, but it is not a potentiometer. It can rotate 360 degrees in any direction. It can rotate in clockwise, also in counterclockwise direction. This rotary encoder is used in many applications to sense the angular position and the direction of the rotation. This electromechanical device is useful in multiple applications like motors, robotics, industrial automation, and as a user interface in many embedded systems. If you observe closely, I am rotating this knob in small steps. These small steps are called as a detents. Each encoder has predefined number of small steps or detents. You need to check datasheet for that encoder to know how many detents it has. This is the encoder from Bornus and it has 24 detents. When I rotate this encoder in 24 detents, then I will complete one rotation. To know the direction of the rotation and number of steps I rotated through, we have two output signals, signal A and B. By verifying the output waveform on signal A and B, we can know the direction of the rotation and the number of steps we have rotated through. Let's see the working principle of rotary encoder. Rotary encoder is not but two rotating switches which get closed and open during the rotation. By detecting the event on these two switches, we will come to know the direction of rotation and number of steps. Rotary encoder has three terminals, A, B and C. C is a common terminal and is connected to ground. Terminal A and B are pulled up and connected to VCC with the help of these two resistors. We observe output on terminal A and B. As terminal A and B are pulled up, so we normally see high output on these two terminals. During the rotation, these switches get closed and generates low pulses. By observing these low pulses, we will come to know the direction of rotation and number of steps. To understand it better, consider internal construction of rotary encoder. Here on the paper, I had drawn the internals of encoder. For simplicity, consider this encoder has only 4 detents. The circular grooves drawn on paper by pencil are the 4 conducting contacts of copper, and these are connected to terminal C. Terminal C is grounded, so these 4 contacts are also grounded. The red matchstick is a terminal A contact and the green matchstick is a terminal B contact. Terminal A and B are pulled up, so ideally we have high output on terminal A and B. In stationary situation, when knob is parked in detent, the contact A and B are open circuit and non-conducting, so we see always high output on these two terminals. Here I am drawing output waveform for terminal A and B on this paper along with time. Consider a situation where I am rotating knob in a clockwise direction from one detent to next detent. During the rotation, first A will come in contact with this grounded conducting area and will become low. On further rotation, B will also come in contact with ground and will become low. When knob gets rotated further, then A will lose contact first and it will become high. B is still in contact with conducting area and it remains low. On further rotation, B will also lose contact and will become high. At this point, knob has reached to next detent and it get parked here. So output on A and B will remain high, still no further rotation happen. Let's suppose if I further rotate this knob in a clockwise direction, then same pattern repeats for this next detent conducting copper area. And we observe same waveform. First A will go low, then B. So this is the waveform for clockwise rotation. A waveform is leading to B waveform. In simple words, A will go low first, then B will go low in a clockwise rotation. Consider another situation where I am rotating knob in a counterclockwise direction from this detent to next detent. In counterclockwise rotation, B will first come in contact with this grounded area and it will become low. A is still not conducting, so it remains high. On further rotation, A will also come in contact and it will become low. When I rotate knob further, B will lose contact and it will become high. After some more rotation, A will lose contact and it will become high. This is what we observe on this waveform. If I rotate knob again in a counterclockwise direction, then same pattern repeats, making B low first, then A. So we get this waveform as seen here in a
counterclockwise direction. If we compare both clockwise rotation and counterclockwise rotation waveform, clearly in a clockwise rotation A waveform leads to B, and in counterclockwise rotation B waveform leads to A. In simple words, in clockwise rotation A first go low, then B, and in counterclockwise rotation B goes low first, then A.
This is the working principle of rotary encoder. Now we will observe actual output signals of the rotary encoder. Here I am connecting terminal A and B to the VCC through pull-up resistor, and I am connecting terminal C to the ground. This is the expansion board I have developed for rotary encoder. I am connecting terminal A and B on the board to VCC, so I don't need to reconnect here. I just need to provide VCC and ground signal to the board, and I can take actual output signal A and B on these headers. So I'm connecting signal A and B to the logic analyzer, and I'm providing power supply from the MSP430 launchpad board. Now I'm rotating knob in a clockwise direction, and I'm capturing the signals on LA. Yes, we are getting the pulses, so let me zoom in here, and yes, here we can see that signal A is going low first compared to signal B, and A signal waveform is leading to B signal. We can observe same pattern everywhere in the clockwise rotation. A goes low first, then B. Now I'm rotating knob in a counterclockwise direction, and I'm capturing signal here. I'm rotating the knob and we are getting pulses here. Let me zoom in here. Yes, here we can see that signal B is leading to the signal A, and in counterclockwise direction B will always go low first than A. So if we compare both clockwise and counterclockwise waveform, in clockwise A always go low first compared to B, and in counterclockwise B always go low first compared to A. In other words, in clockwise A waveform leads to B, in counterclockwise B waveform leads to A. This is the simple operation of rotary encoder. Now I am interfacing rotary encoder to MSP430 microcontroller. For this I have choose MSP430 FR2433 launchpad. On MSP430, each port pin has internal pull-up and pull-down resistor. We just need to enable that. For this interface, I am enabling internal pull-up resistors. So I have removed the external pull-up resistors, and I am just using these two RC filters to filter out the mechanical chattering and directly feeding this signal A and B to MSP430 GPIOs.
This is the code I have written to interface rotary encoder with MSP430. Here I am using pin 4 and pin 7 to connect signal A and B. To interface rotary encoder, there are two ways. First is polling method and second one is interrupt method. In polling method, we are continuously reading GPIO, and based on that, we are taking the decision. This method has certain drawbacks. Controller needs to continuously scan the GPIO after certain interval of time. This will unnecessarily consume controller processing power and execution time. Another method is using interrupt, where we get external GPIO interrupt whenever signal get changed, and based on that we will take the decision. So interrupt method is event driven method and save lot of execution time of loading the controller. Here I am using interrupt method. I am configuring falling edge interrupt for GPIO 4 and 7. On MSP430, each port pin has external interrupt and we need to configure and enable it. Whenever signal A or B will go low, it will cause interrupt and execution will come to this interrupt service routine. In this ISR, first we are checking which signal has caused interrupt, and based on that we are checking status of other signal. For example, if interrupt is received for signal A, then we are checking if signal B already has gone low. If yes, then knob has been rotated in counterclockwise direction. Same case is with B signal. If interrupt is occur on signal B and if signal A is already low, it means knob is rotated in clockwise direction. Here we are setting clockwise and counterclockwise flag which are used in main loop. Along with this, we are setting one variable count in this ISR. In clockwise, it is get incremented, and in counterclockwise, it is decremented. Along with ISR, we are configuring UART to transmit data on serial terminal. In main, we have while loop where controller will wake up upon interrupt, and based on direction of rotation, it will transmit data on UART. Let's download the program and run it. Oof! I forget to connect Launchpad to PC. Let me connect it and retry. Now code is downloading. Let me first debug and check code is running fine. I am placing breakpoint in ISR and I will check I am receiving interrupt after rotating the knob. Breakpoint is placed. Let's start the execution and see if I get the interrupt. Now I am rotating the knob on encoder. Great. Breakpoint get hit. I am receiving interrupt. Code and connection are working fine. Now let me remove this breakpoint and resume the execution. Now I will open the serial terminal utility and check if I am receiving the data. MSP430 Launchpad has application USB to UART along with debugger. I am using same here. Let me open Launchpad application UART terminal. It is port 4, baud is 115200. Then open the port. Yes, we are receiving the data. Let me rotate the knob in clockwise direction. Great, it's working. Output is clockwise and count is incrementing. Now let me rotate in anti-clockwise. Yes, count is decrementing. Let me rotate again clockwise, then anti-clockwise. Great, rotary encoder is working fine. Rotary encoder can be great to create user interfaces in embedded system. We can use it to take input from user. We can replace keypad in many applications with rotary encoder. If you like this tutorial, then please like this video and subscribe to this channel to get more videos on different topics in electronics. I am providing link in the description to download this code. If you have any query or question, let me know in the comment.